All right, let's go ahead and look at exercise 11, also from section 2.5, I believe. Um, so given a physical context this time, we have a tank that has a radius, basically a spherical tank. What we're really going to focus on is what the variables stand for here. So our independent variable H stands for the height, basically the depth of the water in this tank measured in feet, and V stands for the volume measured in, does it say what it's measured in? Or do I get to interpret that? I believe it should be cubic feet, but I don't see it's not called out specifically. But we'll assume cubic feet unless we see otherwise. So first question we're asked is what instantaneous rate is the volume of water in the tank changing with respect to the height? So we wanted the instantaneous rate of change of volume with respect to the height. So that would be dVdh, or if you prefer, v prime. So whichever way we want to look at it, we need a derivative of this function. So what are we going to need to find this derivative? So there are a couple of ways to go about this. We could use the product rule here. It would absolutely work. But I think there's a way around that. And what I mean by that is this. If I distribute here, so if I multiply, if I distribute this, what do I get? I get 4 pi h squared minus pi over 3 h cubed. So hopefully now that you've seen this, we've kind of circumvented having to use the product rule. I believe now we can just get away with using power rule. So what is v prime of h now? What's the derivative of 4 pi h squared? So by power rule, that's going to be 8 pi h. And pi over 3 times h cubed, that's going to be pi h squared. So 3 pi h squared over 3, that becomes pi h squared. And we are asked about a specific value of h, so that's 1. So v prime of 1 equals 8 pi times 1 minus pi times 1. So that comes out to 7 pi. The last thing we're asked is what are the units on this quantity? So I already wrote this as dVdh. What are the units of volume here? So we said they were going to be cubic feet. And what are the units of height? Those are going to be feet. So might seem kind of strange, but couple ways to represent this unit here. So it's going to be a rate. So we got our units are going to have to incorporate both these covariant quantities. So what I have written here is this rate of change is going to, the increase is going to be 7 pi cubic feet per foot of height of the water. Or it's also correct to say square feet, even though that might obscure the fact that we're talking about a rate of volume, a rate of change of volume with respect to some linear distance. But either one of those units is fine. Numerically, the 7 pi is the rate of increase. All right. So now suppose the height of water in the tank is being regulated by an inflow and outflow. So the height of the water is given by this rule. So now it's going to get a little more complicated, but now because now h is not going to be the base variable here, h is going to be governed by time. So now because of that, let's rewrite our function here. So up here, I'm going to kind of squeeze in an h there to show that the function they originally gave us is volume as a function of height. But now we're going to have this volume as a function of time, which is equal to pi thirds times h squared. So I'm basically going to drop in this new expression for h. So pi thirds times sine of pi t plus 1 all squared times 12 minus h, which is sine of pi t plus 1. Or would it make our lives easier if we just went with this? So 4 pi h squared minus pi thirds h cubed. Let's try it. So v of h we said was 4 pi h squared minus pi cubed or pi thirds h cubed. Sort of guessing here, but I think this will still make our lives easier. And I want to be clear, I'm not saying easy, I'm saying easier. I mean, no matter what way we always set this up, we're going to have a lot to keep track of. So here's V of t. So now, I haven't even looked at what we're being asked. So t is measured in hours, h is still measured in feet. At what rate is the height of the water changing? And I've made this way too hard on myself. Should have looked at what we were being asked. At what rate is the height of the water changing with respect to time? So don't even need to involve volume right now. I'm asking for the rate of change of height with respect to time. That's going to come directly from taking the derivative of h. So what is the derivative of sine? That is cosine. But we have an inner and outer function here. So our outer function, I believe, will be the sine function. The inner function will be pi times t. So the derivative of the outer function will be cosine, but I want to leave the input intact, so cosine of pi t. And then I want to multiply that by the derivative of pi t, which is pi. So that's pi cosine pi t. Okay, and then we're also being asked about a specific value there. So h prime of 2 equals pi times the cosine of 2 pi. What is the cosine of 2 pi? That comes out to 1. So what I get here is pi. And we're not asked for units, but we should probably give what the units are. So h prime of t here, that's going to be a rate of change of height with respect to time. So height is measured in what? Feet. And they said time was measured in terms of hours. So this derivative here, this is a rate of change of feet per hour. So for any small change in time, the depth of water, the height of the water is going to increase by 3 times whatever that small change in time is. Part C, continuing under the assumptions of B, at what instantaneous rate is the volume change with respect to time? So now we need all this other groundwork. So now I'm not going to write these things out because we're kind of building up. We already have all the pieces, but what I want to be sure is that, I'll draw my block diagram again. Now my base variable is time. Time somehow gets translated to a depth of water. And then from that depth of water, I can translate that into a volume based on that depth of water. So the volume is a function of height, which is a function of time. So if I want to find, now I'm being asked, what's the instantaneous rate of the volume of water with respect to time? So how do I get that? That's going to be chain rule. So I'm going to take a derivative with respect to time of this, and that's going to give me the derivative of the outside function volume with respect to the height as a function of time, multiplied by h prime of t. And again, I want to evaluate this at time equals 2. So v prime of h of 2 times h prime of 2. So I think we have, hopefully, I think we know we have some of these pieces from before, but let's take a look. We know that h prime of 2 is what? Just, pi feet per hour. Do we know what h of t is? I believe we can find it, or h of 2. h of 2 is equal to sine of 2 pi, plus 1. Sine of 2 pi is 0, so this comes out to 1. So I know that h of 2 is 1, which means I need to know what v prime of 1 is, which I believe. Oh, how convenient. That was the very first thing we found. V prime of 1 is equal to 7 pi cubed per foot. So now I can basically fill the rest of this in. V prime of h of 2, which is v prime of 1, times h prime of 2. This comes out to be 7 pi feet cubed per foot times pi feet per hour. So this is going to come out to 7 pi squared what, though? I believe this feet cancels this feet, and we get cubic feet per hour. So does that make intuitive sense, though, with what we found? So the instantaneous rate we found is the rate of change of volume of water with respect to time. Is feet cubed a measurement of volume? Yes, it's a distance cubed. Hours, that is a measurement of time. So I think this unit and this measurement both make sense. And finally, part D. What are the main differences found between the rates found in A and C? So the rates in A, we'll go back to the slide and talk about both of those. The rates in A, the rates are a direct result of kind of what rates, of what quantities you're looking at. And in part A, we were talking about what's the rate of change of the volume of water with respect to the height. So that's where this feet cubed over feet came from. And in part C, we have feet cubed per hour. So these rates basically, they're constant. Basically, one is a consequence of the other. And what I mean by that is when we start multiplying these rates together, we're not just multiplying those numerical values, we're multiplying the rates. So since the rate we got from A, has feet in the denominator, and the rate we got from the inner function has feet in the numerator, those are going to cancel. So now let's think about this in terms of just the quantities. The outer function gives a rate of change of feet cubed per foot. The inner function gives a rate of change of feet per hour. So if I multiply those together, basically that, intermediate function, it's that, height is measured in feet, that unit is going to fall away. So our final rate is going to be an instantaneous rate of change of the volume, feet cubed, with respect to time, hours.